Okay, hi. Today I'm going to do two demonstrations, and we're going to review a bunch of stuff that we've already covered, and we're going to cover some new stuff. I'm going to talk for a little bit, and then I'll stop the video, and then I'll do a demonstration on a video, and then another one. Your job in this is going to be to write 2 CERs. So for every demonstration I do, you're going to write a CER. It's not really a CER anymore, right? Because that's claim, evidence, and then reasoning. And usually you do make a claim and then do an experiment. And we don't have that option anymore. So I'm going to do the experiment. You're going to observe it. So your CER is really going to be observations and then explaining it, reasoning. The reasons why something happened. Okay, so I think that I am going to give you every bit of information that you need. In the videos I'm going to talk, then I'm going to write down everything, all my notes from the video, exemplars of CERs, so you're going to have everything you could possibly need. If that doesn't work, please come to office hours. Okay, so right now I'm going to talk and I'm going to review some things you don't know. So I'm going to call that review, and then I'll try to remember to say, okay, we're done with the review, now we're going to talk about some new things. There aren't that many new things, but everything, you need to be sure that you're clear about everything that I'm going to say today. And I'm going to try not to take too much time. I've already used 2 minutes, so here we go. Review. You know that we're talking about atoms. Every atom has a tiny little speck of a nucleus in the middle. And the nucleus is where the protons are. Protons have a positive charge, so every nucleus has a positive charge. And it's in the middle of an atom. Around the outside of that is the electron blur. The electron blur is a blur of negativity because electrons have a negative charge. Right? So every atom in the universe has a speck of positive in the middle, a blur of negative around the outside, and those electrons can move. That's a point of emphasis. A lot of people didn't get that in the question in the last assignment. So you just need to understand that electrons are blurry because they can move all around the atom. And in metals, which are wicked wimps, they can actually move from atom to atom. They can flow. Okay, so we know they're protons, we know they're electrons. Protons are positive, electrons are negative. We know about the electromagnetic force. Protons and electrons attract each other. They will tend to move toward each other if they can. That's the electromagnetic force of attraction. The electromagnetic force of repulsion is electrons and electrons, negative and negative, they will repel each other. So if you have something with electrons in it and you move something with a negative charge toward it, the electrons will actually move away, right? They can actually go to the other side of the atoms, and we're going to see that happen. We're going to see evidence that happened today. Okay, what else do we need? So that's the electron force of attraction, the electron force of repulsion. Oh, some things hold on to their electrons very tightly, and they have such a strong pull on electrons that they even go after electrons that are from part of other atoms. We call those the bullies. Bullies can steal electrons away. They pull on electrons very hard, as opposed to wimps. Wimps don't hold on to electrons hard, and they can have them stolen away. And we saw this the other day. Rubber balloon, bully. Glass window, right? Sand, wimp. Bully steals electrons from the wimp. When that happens, the bully started out with an equal number of protons and electrons, an equal number of positives and negatives, ripped away, stole more negatives, so now it had more negatives than positives, and the balloon had a negative charge. The wimpy window lost electrons. It started out with an equal number of protons and electrons. It lost electrons, which if it lost negative, then it became more positive by default, right? It started out with an equal number, lost some negatives, so what was left was more positives than negatives. Okay, that's review. New stuff. If an object, well, I guess I already talked about this. So if we have a balloon with a negative charge and we move it toward a piece of paper or something like that, the electrons in the paper near the edge will actually move around to the other side of the atoms. And I did a drawing that I'll show you later. So we'll actually end up with more protons, right? A concentration of protons near the edge of the paper, because as this comes closer, the electrons, they don't go all the way across the paper because they're held in the molecules, but they actually move to the other, to the other side of the molecule. So the edge of the paper would be positive toward the balloon and be attracted to the balloon. Okay, so that's one thing. And we call that an induced charge. Okay. That was pretty complete. That's mostly what I wanted to say. That's an induced charge. Metals are wicked wimps, and they actually hold their electrons so loosely that the electrons can flow from atom to atom. So if a strong negative charge comes near this can, the electrons can actually run to the far end of the can. Right? So the can itself would still be neutral because the can didn't lose electrons, but these atoms down here would have lost electrons to that end of the can. So this part of the can would be positive because the negative charge flowed away, and there'd be a concentration of electrons down here, so this end would be negative. Okay, so we call that an induced charge. Okay, that was 7 minutes. I'll be back with a demonstration.